Okay, let's begin. So last time we talked about partially the inequality and probability bounds, right? And we have reviewed a lot of important inequalities. Those inequalities will have been used. This is a generalized Bernoulli inequality. This is just the very common inequality: 1 plus x is less than e to the power of x. Okay. We also see something like the Boole's formula and unibound, right? And also the the mutually independent events. We have this bound, okay, which I believe you have seen that before in probability theory, but this is a recap. If it's independent events, E1 to EK, then you can use a tighter bound. Okay, otherwise just use a union bound. And then we talked about several important inequalities that people have been heavily used. So you need to know these inequalities. The first is called a Markov inequality. The second is called a Chebyshev inequality. And the third is called a Chernoff bound. And these things should be memorized. Okay, so you can derive them, but if you don't memorize them, you will not immediately say, hey, I can use this bound immediately, right? So these bounds should be memorized. And then we also look at what's the expectation, what's the variance, and we know that the variance can be computed as your random variable squared expectation minus the expectation square. Okay, this conclusion should be memorized. And we also know the linearity of expectation. We also have another linearity for variance, but that only holds for pairwise independent variables. If the variable xi, xj are dependent, then you cannot use this conclusion. Fortunately, a lot of the times we have independent assumptions. We will see that in the streaming algorithm we'll talk about in the next set of slides. Okay, so where we'll see we'll use a hash function to make sure even the input are kind of not so random, right? So we can hash them to random domain to avoid the worst case. And so there are three inequalities that you need to memorize. The first is called the Markov inequality. Markov inequality for the random variable, it should be non-negative. Okay, so this x should be non-negative. Of course, the a should be some positive number, right? And so if you wanna say, hey, my random variable x is larger than a, right? What's the bound for the probability? So the probability is bounded by your expected x value divided by a. Okay, so that actually bounds your value to be, let's say your expectation is 10. Then how likely will be way larger than 10? Let's say 100. It's unlikely, right? If you divide 10 by 100, it's 10%. Okay, for 1,000, then it's only 1%. You can see that it gives you some bound on how large you can go beyond the expected value. Right? The second is Chebyshev inequality. Chebyshev inequality requires you to know not only the average value, right, the mean of the random variable x, but also the variance. Okay. So for this reason, but the form is like it's a random variable, how far you are from the mean, right? And if it's more than c further from mean, the probability is going to be divided by c squared. Okay, it decreases fast with c. Right? And but here we are using variance divided by this. Okay, in the Markov inequality, it's expectation divided by a. Right? Here it's variance divided by c squared. Okay, and the difference is also that Markov inequality only for like counts, this kind of non-negative random variables. While for Chebyshev inequality, you can use it for any random variables. You can go to negative value. Right? It's just how far it is from the mean. And even for positive values, this is going to be tighter than the Markov bound because you know the variance, you use additional information, right? And then we see the law of large numbers, which means here we are not just worrying about one random variable, right? We have independent samples. We flip a coin and we take the mean. Okay? How far away they are from the actual mean of your random variable, right? So this is we can see that it's your variance divided by n, right? So the more samples you have when you take average, the smaller the variance. Right? If you have 100 times more n, then your variance is reduced by 100 times. Okay? And then we came to here, right? So we talked about Chernoff bound, and we didn't have enough time to finish that. So yeah, what is Chernoff bound? Okay, Chernoff bound is actually it's a more general, but we are looking at something like Bernoulli variables, right? So it's like you have many trials. Each trial has a success probability P and a fail probability 1 minus P, okay? And you have X1, X2, it's like a flip a coin, and the head is maybe 50% or 48%, etc. Okay, and this is from the same Bernoulli distribution. Okay, and you are flipping a coin for n times, and then you want to count how many heads you will see. Right? So this is the problem setting we have. Right? So you can compute the sum. If you have a head, it's 1. It's tail, it's 0. The summation is how many heads you see, basically. So we can write this expected value of the summation, this S, expected value S as n, okay, which is mean, right, basically, right, equal to NP, right? So this is saying, hey, if your let's say your probability to have had is, let's say 60%, right? And if you try n is 10 times, right, 10 times flip coin, then in expectation you will see 6 heads. Right? So this is very easy to reason if you think about all right, so expectation S is equal to expectation of the summation, right? So based on linearity of expectation, it's equal to expectation of each xi, right? And each xi is actually P, right? It's because expectation is computed by probability times your value plus probability times your value, right? This is 0, this is P, okay? So in general, keep in mind Bernoulli variable, right? This P is also expectation, okay? So you just sum this P n times, okay? That's why you have NP, right? So you can strictly derive this, not just by intuition. Any question about this, how we get M equal to NP? Okay, if this is okay, then we will give our Chernoff bound for the binomial variables, okay? Right. And so binomial distribution is a n Bernoulli distribution, basically. Right? So you try n times, each time the success probability P. Okay? So here, the Chernoff bound is actually decided, which means you need to say, hey, this is my random variable value, this is the mu, this is mean value, right? So you want to say, hey, it go too far beyond your mean. Okay, it's not very likely. Probably to be here, right? You can also say it's too much smaller than my mean. Okay? So we need to decide a direction when we talk about Bernoulli variable. Here in our case, we're talking about, larger than the mean value. Okay, by delta. So this is your mean value. You are larger than the mean value by a delta fraction. Okay, so this is on the right hand side. Okay, we also have another conclusion with minus delta. We'll see that shortly. Okay. So for any delta larger than 0, right, this holds for any delta. Okay, the probability to have this is bounded by this. You can see delta appears 3 times here, which looks pretty complicated, but we will simplify this later. Okay, so let's first think about how we can prove this. Right? Let's first think about how we can prove it. And before we do this, let's get some intuition. Why such a complex thing is interesting, right? This is because this delta, they are constant. Right? They are some how large you allow it to be going beyond. Okay, so we can think about this as constant, right? So what remains is actually this n. Right? M is equal to np. Right? So np. What does this tell us, right? So this tells us that as you increase n, right, and this probability is going to be less than 1. Okay, and as long as you try, you try many n random values, right? Try many times. Okay, so this value will decrease exponentially, right? So if you have some number that's less than 1, then you go to the power n. It can go really small with enough number of tries, right? Which means if you try enough numbers and then come to the mean, right, the probability that you are too far away from the mean is going to be very low. And this may not be obvious, but let's think about 0.5, right, or 0.1 n. These two are either more intuitive. Okay, so this is like each time you divide by half. This is 1 by 2, n equal to 2, 1 by 4, right, 1 by 8, and you can see this decreases happens each time. It's happens quickly. So this 0.1, then each time you add another 0.01. If you add another n 3 times, then 0.001. So you can see this really decreases exponentially. But don't be confused, don't be fooled by this number 0.1, 0.5, etc. Okay. the key here is that it's exponential. As long as this number is less than, as long as this number q is less than 1, okay, you can always bring it down to almost 0, decrease exponentially. Okay? This is really fast until it's faster than limit, okay? And until you hit the almost 0, then you decrease it. Okay? So as long as this value is any value less than 1, okay? If it's a little bit larger than 1, it goes to infinity. Okay? It's exponential. Okay? And the only case is if it's exactly 1, then you stay out. Okay? 1 to the power anything. Right? So that means if this probability bound is less than 1, then as long as you try enough times, right, and enough times, okay, then you can bring the probability to be really low. Okay. Any question about this theorem here? Okay, I think it should be fine. So let's continue. But how do we prove this? This looks pretty complicated here. Okay, how do we prove this thing? So what we do is we use one conclusion. Right? So if we think about the lambda is some positive number, okay, lambda is some positive number, then what will be the value of exponential to the power lambda, right? So we know that e to the power x is something like this, right? So something like this, where this point is 1, 1x is 0, okay? And this goes infinitely close to 0, okay? But one thing you can pay attention is this function is a monotonically increasing, which means if you get two values here, let's say you get any two values. This is x1, you get x2, okay? And then you map here, this is maybe your y1, okay? This map to here, y2, okay? So we have a guarantee that if your x1 is less than x2, then y1 is also going to be less than y2, okay? Then y1 is less than. Right? So this does not change your sign, basically. Right? So if your originally your x is monotonon, right? And then after you take e to the lambda of x, so the relationship is still kept. Okay, I hope you can see. So in this reason, we can just put left hand side, right hand side to x. Right? We'll get this. Okay, e to the power of lambda s, e to the power of lambda is right hand side. Okay? So the reason we are doing this is because we really want to have this exponential component. We want to construct such an exponential component. And by doing this, actually, we can then see something interesting. So you can regard, so remember, right, because we say that this S is a random variable, right? It's the mean value here. It's a random variable, okay? This summation. Where each value is a random variable, then your sum is a random variable function, which is again the output of the random variable. So if we regard this entire thing as a random variable, okay? So if you regard this entire thing as a random variable, right? And this random variable is going to be positive. Okay, we just see the curve. Right? It's going infinitely close to 0, but it will never be 0. Okay, so this satisfies our requirement of, Markov inequality. Right? Markov inequality says that if your variable is larger than a, the probability expectation divided by a. So you can see this is a to the power negative. Okay, so this is how we get it. I hope you can see that. Any question about this stuff? If you cannot memorize, let's go back to this. Okay? If your random variable, which is non-negative, is larger than a, it's bounded by expectation, then the random variable divided by a. So here we are treating, basically we are treating this as x and this as an a. Okay? So you are getting expectation of this, right? Because this is going to be larger than this. Okay? Expectation of this divided by this, right? It's negative. Okay? I hope this will be clear. Now, using this conclusion, what we can do is let's compute the expectation. So the expectation of lambda s. Remember, s is what? S is summation. right? Summation of xi. Right? So that's how we define this thing here. S is summation. Okay, this is what we are doing for S. Okay, so we can write it like this, because exponential of a plus b, right? E to the power a plus b is equal to e to the power a times e to the power b. Okay, so we can make it a product. Okay. We can here summation above e, okay, can be product after e, because e a plus b, okay, is equal to e to the power a times e to the power b. I hope this is intuitive. Right? Now next you can take a look at, so xi are flip a coin each time, right? So x1, x2, x3, they are all independent. They are generated another random variable, right? E to the power lambda xi are also independent, okay? And so because of this reason, if you have, remember we have a linearity of expectation, right? But we can also write something like this: a times b, okay, is equal to expectation of a. So this is times, it's not a sum, okay? This is times. Okay. Let me try to read this. This is take the product to the power, okay? But this is not linearity, right? This product, this only holds if a and b are independent, which is our case, right? So every variable for different I are independent, right? So then we can time them independent as each time, okay? I hope you can see this. So next, the question is, what is this? What is a let me see why. Right. The next question is, what is e to the power, right? So it's a computation very similar, right? So we know that with probability 1 over p, right? You can take a value 1. Right? When you take value 1, it's p times what? P times e to the power lambda. Okay. Let's see. With probability 1 minus p. Okay. 1 minus p. Right? Your probability. This is your probability. The value is 1. If you put 0 here, right? So this is 1. Okay. So this is 1 minus p. So you sum them up. So it's a 1 minus p plus exponential. Okay. So that's how you go from here to here. Just follow the definition that our xi random variable is this. Okay. Okay. So you'll see. Okay. Yeah, I hope so far so good. The derivation is a little bit complicated, but at least you can understand it. So you may not be able to prove it, but you can follow it to prove the other direction. Yeah, so the e to the power 0 is 1. Okay, anything to the power of 0 is 1, right? So, x can take xi can take two values, right? So if it's 1, then x is to the power 1. If it's 0, then the thing is the whole term is 1. Okay, so that's the probability times 1. Okay. And this is just follow expectation. And then you can take a factor out of p, right? P e to the power lambda minus 1 is 2 times. Okay, and plus 1. This term in the middle. And the next we are using, so I hope you can see why this is the case. So we are using another inequality we talked about, this one. Okay? 1 plus any number that is non-zero is going to be less than e to the power. Okay? By using this, we will see we work at this, right? 1 plus any is going to be less than e to the power. Okay. If you put this as x, treat this as x, you will see it. Okay. So this eliminates, other uninteresting things, right? So the plus 1. All right. So far, what we proved is that the term we highlighted here, which is this term, right, is less than this term. Okay. So then we can say, hey, this term is less than this thing here times this thing. Okay. So it's e. Remember, this is using Markov inequality. So divide by A, okay? And then we have this upper bounded with this, okay? So that's what we have in the next page. Okay? So this is what we have so far. This is divided by A, right? This is what we see at the end. Okay. So far we proved this inequality, but it's still not where we are, right? So we want to have some shape like this, okay? But right now we are here. So how can we continue with that? So you need to get a particular lambda, right? Because this holds for any lambda, right? So this is basically for any lambda. We give a particular lambda so that we can make the form look a little bit nicer. Right now it's too complicated. But the nice thing is that it's all exponential to power something. Right? So apparently we will get something like this, right? So you can see we have a line, okay? So the reason we have a line is that if we put it here, line and E can cancel, okay? Similarly here. Right? So that then things can look nicer. So by putting lambda like this, right? We put this line here, and then this term is here, right? So this thing, line and this they can cancel. We'll see it shortly. Okay. And on the other side, similarly, right? So the lambda is this. Okay. Next, after you can cancel this, but you need to move this -1 also, right? So you get this, and they cancel. It's 1 plus delta, but divide by 1 divided by that, we go to the power 1, which is this thing here, to the power this thing here. Okay. And this term is even more interesting, right? Because these two terms cancels. There's 1 and -1 cancels. So this is there. So this P there. Okay, P times 1. Right. So you can see by getting that value, we can immediately this 1 is to cancel this. Okay, we get something much simpler to handle. Okay. And then we can this term here has nothing to do with R, right? It's just a time this n times. It's equal to this times n, right? Without it. Okay. And so this is what we get here. And what's interesting is we need to remember what is MP, right? Or what is M. M is equal to MP. Okay, this is what we discussed earlier. M equal to MP. Okay, this is what we see. Using this conclusion, right? So this is M, this is also M. Okay, it's M delta. So we can take this term inside because we have an M taken out. Okay, so this is E delta M, right, which is this term. Okay, for this second term, basically we say, hey, this delta to the power 1 is still delta 1. Okay, so we just have the delta times this thing. So this is why it's 1 plus delta, 1 plus delta. Right. So this basically proves our theorem that we want to show that you are more than delta fraction from the mean. It's going to be upper bounded by this value, which is super complicated right now. But keep in mind, this is NP. So that means your value decreases exponentially. These are the constant because you will give some desired data like 10% or something. So this will be constant. Okay. But this constant here is not easy to understand. So we'll do some simplification to make it more easier to comprehend. Okay. Yeah, so this completes our Chernoff bound proof, where we want to show this for delta is larger than 0, so that we are on the right side of the mean. Okay. Any questions so far? Yeah, the proof is a little bit complicated, but we have assignment. If you remember, we have assignment, active assignment, where we will ask you to prove the other direction, minus. Okay. But don't worry, because we have this slide. As long as you understand the lecture, if you don't understand, you can watch the video again. Okay, you will be able to emulate what we did here to prove the other direction. Okay, it's almost the same. So you still do these stats, make a monotone function, etc. Okay, you will prove the theorem again for the other direction. Well, this is a minus state. Okay. All right. So let's do some simplifications because that constant is super complicated, right? You see here. So how can we simplify it? So we want to show that if your delta is really small, so you want to not to be too far away from your mean, right? A little bit far from it. Right? then your probability drops exponentially with that. This means, hey, if you make data a little bit larger, we square it. So this is the truth. How to see that, right? So we need to use some conclusion. This conclusion may not be easy to see, right? So there's some formula called Taylor series, right? Taylor expansion. Okay, I hope you at least you memorize this. Right? So this is the scope of our lecture. It's a it's calculus, mathematical analysis. Yeah. But each function of x can be Taylor expanded into a series, right? Summation of a series. Okay, and in particular, for example, for this line 1 plus x, which is what we are interested in, right? So what it will be, the value, of course, x should be less than 1. Okay. So what the result would be is, starting from 1, right? If this is 1, so you can see this is x. Because if this 1, this 1 plus 1, 2, so this is 1 minus. Okay. Then you divide by 2x squared. Okay. Plus 3x cubed, right? Minus 4x to the power 4 plus 5x to the power 5, etc. You can go on forever, and if you go to infinity, the value is going to be 1. Okay? So that's a conclusion that you basically, if you memorize some of the common ones, sine, cosine, epsilon, lambda, ln, okay? So that would be easier for you to do some analysis. So this is not requested here. So unless when you see this, you need to know, and you can look up the like a formula book. Okay. So how do we get this? Right? So previously we told you that this is equal to what? It's equal to delta, right? Minus 2 delta square. Okay. Plus, let me see. Plus 3 delta cube. Okay. Minus 4 delta to the power 4. Because we are considering small delta, right? If it's 0.1, then the 4 times is already 0.0001. Right? We ignore the rest. Okay. Okay. For this, if we times delta, right? So the first term is 1 times this term, which is here. The second is if we times delta, right? Then it becomes delta square, right? Which is this thing's times delta, minus this term times delta. Right? This is cubic, and then this term times delta. Okay, it's a plus 3 delta to the power 4, and minus this term. But more than to the power 4, we probably can ignore it because it's way small for small delta. Now you can see the conclusion. Right? So this delta is this term. This plus 2 delta is really 1 minus 1 by 2. Okay, and this term minus 6 is really 1/3 minus 1/2. Okay, right. So this is this is 6 to the power 2 minus 6 to the power 3. Right? That's why it's minus 6 to the power. Similarly here, you can see this is 12 to the power 3, and this is 12 to the power 4. Then because this time this is plus sign, so it's a plus 12, right? Because it has one difference. And this can go on. Okay. So if you do Taylor expansion for this term, it will be this is 1, this is 1 by 2, this is 2 by 3, this is 3 by 4. And then you have minus maybe 4 by 5, 20. Okay. Delta 2 by 5, etc. You can go on. But because we are considering a small data, so if you to the power of very large values, you can ignore. So now let's take a look at this term. Right? So we know this term is equal to what? This term is equal to this, right? Line this. Okay, because this constant can be to the power. Okay. So because of this reason, this term is equal to exponential of this, right? So that's a constant. Okay. So we have exponential sign of this. And then what will be the value here? Right? So exponential divided by this term. Right? So then it's, if we have e delta divided by this. Right? So this term cancels. Okay, this term cancels, and this becomes negated. Right? Which is this term, this negated divided by negative plus. Okay, plus and negative. So you can see that finally we can get a conclusion like this. Right? So we are saying, hey, this constant. If you remember what we are doing, we are talking about this constant to the power. Okay? This constant here is equal to something like this. Right? If you ignore too high order, it's e to the exponential delta square. This decreases fast. Okay, it's e to the power minus x is something like this. Go very close to 0. Okay? But e to the power x is this direction. Minus x is this direction. Right? The other direction. So this goes really quickly, right? So as your delta becomes larger, it squares and then it's negate. Okay, it decreases really fast. Okay, so probably that your delta fraction larger than your mean value decreases quickly. So this is one conclusion. So probably drops exponentially with delta square, not even delta. Okay, so we have this conclusion because it's a constant, right? So this is a constant here to the power n is just to add another term n. Okay, all right, so this completes our conclusion of this conclusion after simplification. Any questions? All right, so let's look at the other case, right? So what if, so what if the delta is some value that is relatively large, right? So here it's really large, okay? E is 2 point something, right? So 2e is almost a 5 point something, minus 1 is still 4 point something, okay? So when your delta is close to 5, for example, or larger than 4, right? Can we even get something more interesting? The answer is yes, right? So if you do this, then we can go from here to here. Right? So I think I should have cleared it. We can go from here to here. So how do we see that? So firstly, we can enlarge this term to e1 plus delta. Right? Of course, you times another e here. Basically, you times another e here. It will be larger because e is larger than 1. It's 2 points. Right? And so this gives you 1 plus delta n. So the sign is larger on the right hand side. Okay? So this term and this term is still this term. Right? So this is how we get from here to here. Okay. And given this, right, we can use our conclusion where data is relatively large. Okay, larger than some value, then we can use this term, which is really looking nice. Okay, so because if you have this and 1 plus delta, 1 plus delta, which is this term also this term, you put 1 to this is going to be larger than 2. Right? Larger than 2. So you know, e divided by something larger than 2e, right? It's going to be smaller, right? So the sign, because it's on the numerator, right? So it's going to be smaller than 1 by 2. Okay. So basically, this term is going to be smaller than or equal to 1 by 2. Right? So that's why we have this conclusion. This is 1 by 2. Okay. So why is this interesting? This is saying, hey, you have something like a 2 to, it's like whenever you add another n a little bit larger, np, add a little bit n, then you divide another 2 or something. Right, so this is cleaner. This is easier to comprehend than some complicated term like this. It's basically a 2 with some term, constant term. Okay. And there are different ways to simplify Chernoff bound. So this is actually not the most popular Chernoff bound form. Okay, let me see whether I can give you some. So the most popular Chernoff bound form is actually this one. Okay. I don't remember where we get that earlier, but if you go to our this paper also uses bounds. So do some derivation on probability, and let me see. Okay, so this is a Markov inequality. This is the most popular form of Chernoff bound. Okay, let me see this. Okay. So this is actually a more popular form. Okay. 1 plus delta. Okay. 1 plus delta times a new value. It's going to be exponential. So if you're, this is what we almost see, right? Like that. But the other side, between 0 and the 2e. So actually, we can show strictly it's upper bound by delta. We don't have to tell somewhere. Okay. We can also prove this. Okay. But here because this proof will be a little bit more complicated, we just simplify things. Right? So this is the more popular bound that we can. But in whatever case, you can see it's a 2 something. Right? Each time you increase your mu. Mu is NP. Here mu is N. Okay. As long as you increase N, you are dividing a 2 or divided by E. Right? You decrease exponential. So that's an intuition what Chernoff bound is telling. Okay. Let's see what we can close this. All right. So far what we see is only on the right-hand side. Right? What if you are less than me, right? But you are not too much less than me? Right? So here we of course we are not we have a bound, right? So we cannot go beyond the bound. Yeah, because go beyond 1, then no. So gamma is no. If go beyond 1, then you are going to the negative side. Right? So we still want this to be positive. Usually, when we use it, we think it's somebody positive, right? Because this is a count. Right? If you think about it's 0 or 1, right? It can go. S cannot be negative. No matter how many 0 or 1 plus together, it cannot be negative. So that's why we have a 1. If gamma go beyond 1, then the right-hand side becomes negative. S is not going to be negative. So this is always going to be 1. Right? It's always going to be 0. Right? You cannot say S is less than, let's say, a negative number. Right? The S is always going to be positive. So this will be 0. Okay? So that doesn't make sense. So we have a bound, right? Gamma, but it cannot go beyond 1. Okay? In the other case, we have a similar form, right? So the form is quite similar. Okay? I think this is probably minus, because there's a type of, this should be minus. Okay? And e to the power minus gamma. Pay attention when you do your assignment. This is minus, because this is minus. And so we have some similar theorem. Right? So it's decreasing quadratically. This is always quadratically, okay, on the small left-hand side. On the right-hand side, if you remember, we just see, so linearly with delta. Right? So if it's large enough. But for the left-hand side, it's always quadratic to gamma. Okay? This is gamma on the left-hand side, delta on the right-hand side. It's delta minus gamma. So yeah, so this proof is very similar to our earlier proof. Okay, let me see what it is. Basically, you need to emulate how we prove the plus delta side. Right? And go through this process and go through this process. Okay, and actually reach here. But you will go through the same process for minus number. This will be 1 minus gamma, 1 minus gamma. Okay, and then you will finally see that. Okay, and you will be able to simplify to this string. So this will be in the last question or the second question. I think for the written assignment, we have 3 questions. Maybe this is the second question. Okay. Anyway, so after this slide, you should be able to do assignment 1, which is due, I think this Friday, right? So yeah, you have 3 days to just emulate this and complete that. Okay. All right, so I think that completes our bound slide. Okay. Any questions so far about this slide? Okay, if not, let's take a 5-minute break because we see a lot of mathematics. So it may be a little bit headache for some students. Let's take a little bit more than 5 minutes. Right? So it's now 5:43. Let's come back at 5:50. Okay, thank you. Okay, let's begin. So, so far what we have seen are the important inequalities. So they are very basic for if you want to do research on, for example, randomized algorithm. Okay, so basically everyone should know these. And one important application of randomized algorithms in when you learn some statistics of a data stream, right? So if you keep seeing data coming like in a streaming manner, right? But you cannot keep all of them, right? So because it's keep coming every day, right? For example, of course you can keep simple ones, right? So like if you're having a search engine like Google, you can keep the search logs, right? But sometimes if you don't have a lot of resources like a data center, huge amounts of disk, right? You probably don't want to keep all the search history of other people, right, on your own disk. Let's say if you only have one server, one machine, right? For that reason, you need to keep a so-called sketch, right? It's a compact form of the summary of what people searched. Okay, but from that sketch, you can recover the information of the original stream with reasonable accuracy. Okay, but usually those sketch are the sketch for a particular metric, right? Statistical value measure. Okay, one measure have one particular kind of sketch. Okay. All right, let's take a look at this streaming model, data model, streaming setting. Okay. We assume that there are n data items, but this n can increase, right? So A1, A2, A3, all the way, one at a time. Okay, you will see a lot of data. Right? Assume at this moment you see n data set. This is what we are talking about. Okay. But these values, you can map them into integers, right? So like apple is 1, banana is 2, right? Orange is 3, right? So you can map those values into integers. Let's say their IDs, for example. Then their IDs belong to a domain from 1 to all the way to n. Okay, there are n different values basically. They can count one at a time. And in order to represent how many, represent the number ID of that, right? So the minimum is log n bits. Okay, you need the log n bits to represent n different values. Okay. This is easy to understand, right? So if you have 4 values, you need 2 bits, right? 0, 0, 0, 1, 1, 0, 1, 1. Okay. If you have 8 values, right, you need the 2 to the power 3, which is 8 bits. Okay. If you have 16 values or 17 values, you need 4 bits. If you have more than 16, 17 values, then you need 5 bits. Okay. It's actually going to log in, right? Because 2 to the power of n, 2 to the power of k, how many bits you want, right, is equal to n. You have so many different values, and each have a binary string, and k equal to log 2n. Okay, so that's how you get it. In our computer, usually we will ignore this log n, right? Because you think about it, right? So our integer is 4g, right? 4 billion values. Okay, 2 to the power of 32, right? For a regular integer. Right? So this we think it's large enough. So we think this is a world of 32 bits, right? And we think it's a constant, but actually it's log n. So if you know Java, there's a big integer where you can go infinitely long. Right? So if then in that case, you do need to care about how many bits you are using, how many units, storage units you are using. Okay? So overall, it's a log n, but log n so, decreasing in size so significantly, you can think about it as constant in reality. Because, if you have 1 billion, right, 1 billion, 9 zeros, okay? So this is equal to 1,000, right, to the power 3. And 1,000, it's 1,024 is 2 to the power 10, right? So basically, 1 billion is just a 2 to the power 30. After taking log, 1 billion becomes 30. So this is really small. Okay? So basically, in our computer, we just say, hey, we assign 32 there, right? As a constant, we treat it. Even though it's not a real constant, it increases with n, but usually the n is not going to be larger than 4 billion. Right? Actually, these days, the more popular word is 64 bits, right? Because of the operating system has become 64 bits. Right? You have size t in your Linux or in C++, it's 64 bits unsigned. Then this could become even crazier, right? 2 to the power of 64. You can never exhaust it. Right? So we think 64 can be a safe constant, even though it's actually increasing with n. Because this reason, if you have something, let's say you have a big O notation, right? You have some function of that. Okay. So actually, if you want, you can eliminate a log term. Okay, you can say something like, actually, this is fx times a log term, especially for space. Right? So you have a log, big O count to both time and space, right? Big log x. Okay, you can approximately write, hey, this space is approximately equal to, you have a title here, fx. Okay, so really because we choose this log n as a word, okay, it's a constant. Okay. But for this case, you will see a title. So that's just for notation purpose. Any questions so far about this? All right, so let's assume this log n bit is constant, right? So then this can look easier, right? So, but anyway, so so you don't want to keep all the n values, right? Or you don't want to keep all the n values. Sometimes, let's say you want to count how many apple, orange, right, banana, right? So you can keep 3 counters. Whenever you see an apple, you can add the counter of apple or something, right? But again, you think about, it's not just the apple, orange, right? You think about Amazon, right? There are millions or maybe billions of different products, right? So each you maintain a counter, your computer cannot hold it, right? So our goal is to have a sublinear space, okay? You cannot store something linear to n or linear to m. That will be crazy. You don't have so much space. And sometimes it's open, right? So you never know this number, right? Whenever you see a new product come up, you assign a new ID to it, right? And then this can grow, okay? So preferably, we want the space to be logarithm to the minimum of n, right? So let's say you have 1 billion different products. You want a space that is 30. So this is what we are talking about, instead of 1 billion, okay? And another thing is that we want a faster incremental update, which means I'm seeing streams, right? When I see an plus 1, I can immediately update my sketch, right? The space I maintain for the sketch. I can immediately update it to reflect the change, okay? This is, different from, let's say you have some compression algorithm, you need to decompress the whole file and then take out that file you want, right? So the small file in the middle that we want of a bigger zipped folder, right? So here we don't want to do that, right? We want to do incremental change, and we can change that thing immediately, okay? So this is actually not achievable most of the time if you want accurate answers, right? So what you can do is you can have small error, right, by randomized error. Let's say if I want to get how many people visit my website, right, around 1 million, okay, I can get a small error. Well, around 1 million, but the difference could be less than 1,000, okay? So that can be achieved. But you want to get an exact number, maybe 1,232, right? This is impossible. You want to get that accuracy beyond a small error, you need to pay all the linear space. But if you allow a little bit of error, you can significantly decrease the space. That's the idea of the streaming sketching. Okay, any questions so far about what the streaming algorithms is doing? So the space that it maintains, the structure that for update when you see a new stream, is called a sketch. Okay. Sketch. Okay, let's see a few examples. So basically, this set of slides are giving you some examples of what is streaming and sketching. Okay, let's see some examples. Firstly, let's think about a problem of random sampling, right? You want to sample a number from the stream. Here is the example, right? You see different numbers coming, right? Arrive one at a time. Right? Of course, you can decide, hey, whether I should sample this item now, right? If you just sample the first item or the third item, then a million item comes, right? And you now sample a item that comes after the 10th item, right? This is not gonna be a random sampling. It's biased towards the early sampling, okay? So we want to have an algorithm that can guarantee that my probability of sampling the items in the stream is uniform. How can we guarantee that? Okay? So here we are saying that this is interesting, right? So we are not caring about what the item it is, right? So here each item comes with a weight. Okay? So these AI are not the actual item that we sample. Right? Actual item we sample can be look at it's a value. This is like a key. So it's like if you look at the map and the set, right? You know, in C++ or Java, hash map, hash set, right? So if you look at Python's dictionary and stuff, right? So the difference is you have a red black tree or hash map, right? Associated with each node, you also have a value. The value is not important. The key is deciding how you look at it. Okay. This is similarly, the value, what the actual item, it doesn't matter. When you sample, you associate the values with the sample. This is the key. This is weight. Okay. This is how important this item is. Right? Your sample probability should be proportional to the value. Right? For example, the first item comes with a weight of 2. Right? Let's say this is an apple. The second is the orange, comes with a weight of 1. Right? Then if you sample, the probability you sample A2 should be only half of the probability you sample A1. Okay, these are the weights. Okay. If you truly think they are uniform, then you just give all of them 1. Okay. This is the probability. But when you sample a particular item with, according to the probability, you just take that item into sample. So that's the idea. So this is a little bit different from our setting that we have. So these n values doesn't matter. Okay. It's just a common with values in this case. So how can we do the sampling, right? So to make sure, even though we are not see the entire n value up front, right? So we see one item at a time, right? So what we need to do whenever we see a new data item, an plus 1, we need to decide whether we should sample it to replace the current sample or not. Assume we only take one sample, by the way, okay? And if we do so, what should be the sampling probability that we use this sample to replace the existing sample we take? Right? So that's the thing that we need to figure out. Okay. So the answer is we can do some. So let's do some interpretation. Okay. Let's assume that S, this green S, is summation of all the values we see so far. Remember, they are probabilities. They are weights. Okay, we need to normalize the weights to the probability. So summation is like the normalization factor. Okay? So what we want is at any time, right? Let's say now we see A1, A2 to the AI. I is an any I. Okay. The sampled element AI is sampled with probability 1. So apparently, let's assume that right now I have A1, A2 to AI. Okay. Then we should sample AI with probability proportional to I. So this is the summation of all items. Right? The probability you take I should be this. AI divided by S. Right? Okay. So this looks good so far. So our conclusion is we should do something like this, right? Well, now when we sample stuff, okay, when we see a new item as an n plus 1, what we should do is we compute a new summation, right? Summation, and then we sample this new item with probability this way divided by the current new summation, which is A1, A2, AN, and then plus 1, summed together. Okay. So is this algorithm meaningful? Firstly, let's analyze the requirement, right? So what do you need to maintain? All you need to maintain is a summation, right? With S. Whenever you see a new item, you just add it to the current cumulative summation, right? The space is really constant, okay? When we say constant, actually we are talking about bigger O title notation, right? So actually the S should be logging, okay? If you think about the number of bits. So this does not break our requirement. And secondly, is it easy to update? Right? It's very easy to update. Right? Whenever you see a new item, just sum to S. Okay, sum to this. Finally, it's the operation of sampling is easy. Right? The answer is yes. The operation is easy. Okay, right? So we just have the new summation that we maintain, and then we will see this new value coming, and we just divide them, and that's the probability we flip the coin. And if it's a hat, then we take that out, replace with the current item. Okay, keep in mind we just sample one element. Probably originally already have an element before you sample this, right? Maybe A3. Now you decide whether you should replace AN into A3. Right? So now the sample is AN. Right? The probability is using AN divided by S. Okay. So this looks good so far if you think about the last item you see, right? The AN, the AI you see. But the thing is that, what if I keep it A3 instead of the new item AN? right? Is the probability still correct? The answer is yes. Okay. So here, let's look at the algorithm again. Okay. So if I equal to 1, then you will always sample, right? Because you only have that thing to sample. Okay. When you see another item, j plus 1, right now we have j items. What you do is you change, it's a probability that you change from the current sample, maybe A3, to aj plus 1. So you sample the j plus 1 item, the probability is aj plus 1 divided by s plus 6. That's the new summation. Okay. And you will maintain the new summation. Okay. S equal to s plus 6. But let's see the correctness. Right? So if we use a new index, of course this is correct. Right? Let's think about if we keep the old index, let's say A3, what will happen? Here we think about A3, right? So maybe with 1% probability, we choose this. Right? This is a 1% probability. Right? But with 99%, is this 99% we choose A3 is still correct? The answer is yes. Right? So what's the probability that we keep the old index? Right? So probability is 1 minus this. Okay, 1 minus this. Right? So now keep in mind we have flipped the coin randomly. Each time we see a new sample, we will flip our coin and then decide whether we should take it. Right? Now what's the probability that we take the old item? Right? So firstly, so we take a new item, probably this, right? So this time we don't take the new coin, right? So this is a probability. But previously we also have another probability when we have S. This is by induction. Before we see the new item, this is correct. We say that the A3 is sampled with A3 divided by the old sum. Okay? And then the next action, the next step, we don't take the new item, AJ. That's why it's 1 minus. Now let's take a look at what's the result of this value. So this is S1 is S plus AJ plus 1 minus AJ. Cancel it. So we have S on the top. Okay? And then these two S can cancel. Right, then we get this. So is this probability correct? The answer is yes. Okay, right. This is the new sum after you see the AJ. Right. This is the weight of the A3. You all the same. So this tells us what, no matter which action you take, right, takes a new action, of course it's correct because there's a new sum, this is a weight, right? But even if you keep the old one, the probability is still correct. This is the old weight, this is a new sum. Okay. So what this tells us is that just by keeping the new summation, right? Each time you add a new item to your summation, right? One update, your sketch is just a summation. And the action that you take, another thing that you maintain is whether you take the new item AJ plus 1, right? With this probability, you will take AJ plus 1. With otherwise, you keep the older AI, okay? Keep the older E3. Right? And in both cases, you are correct. Okay? It still respects the sampling probability. Okay, this is the requirement. Okay, so far so good, right? So we just need to use this algorithm with this at the top, right? And do the incremental update. And finally, the sample will be uniform, as if we sample, we see all the data items up front, right? We see the n items, and then we sample them proportionally to the probability. Right? But we don't need to see them up front. We can do a streaming update. Right? Whenever we see new item, we update a little bit, but the result will be the same. The nice thing is that you don't need to see all the data at the very beginning to sample. You can incrementally update your samples. And at any point in the stream, you can take out your sample, right? And you see, hey, well, what's the sample value? It's always going to be correct. So one question here is, why is this useful, right? Because this problem is that we only take one sample, okay? We only take one item. Would that be interesting if we, so usually when you want to estimate some value, right, you will not estimate from one sample. You want to estimate from a set of samples, right? A sample set. Then you see, hey, what are their distribution looking like? What are the, like you do a survey, right? You want to sample a small population, right? So the answer is very simple, right? So here's just one sketch. Okay, one sketch maintains two things, right? So if you remember for this algorithm, one sketch maintains a summation S. Okay, let's do it here. And summation S, and it's a sample you take AI. Okay, so just the two numbers for one sketch. But what you can do is you can maintain a number of things. Right? So you can maintain, you can denote it by A1, S1, let's say we maintain K of them, okay? Keep in mind that each one is independent. We flip the coin independently, okay? The summation actually can be shared because, it's a latest sum. But each time you flip coin to decide whether you should take the next item, this coin flipping is random, okay? So you can keep basically, so this is just one sketch with 2 integers, right? You can keep K of them, then you get a K random samples, right? And then from this K random sample at any point in time, let's say now, I want to estimate some value from the samples. I can do that. I can use these K values and K samples and check their attributes and estimate what I want. Okay. All right. So that's random sampling in a streaming manner. Any questions before we move on? Yeah, I think this algorithm is pretty simple. Right? So the important thing is to understand why this is correct. Okay. So the important thing is that you do not want to see all the samples up front, right? It's like maybe it's always ongoing, right? Like Amazon, right? So you see the product ongoing, who is buying what, okay? It will never end, right? But at any point of time, I can get a sample of my customers and look at the attributes and know what's happening, what's the distribution. There's a question asking me, what if, what will happen when AJ value is high? Right. So this is what happens, right? So if AJ value is high, then the probability sample this AJ is high, right? It's just respects this, okay? It's an independent question, I think, right? So this is our target, right? If your AJ is 10, the other is 1, right? Orange is 10, apple is 1, then maybe you will sample 10 oranges, then just 1 apple, okay? So, but we will always respect this rule, right? Do you answer your question? And if you really want to unbias the sampling, right, just to give everyone weight 1, okay, right? That's it. Right? So it's like everyone has the same weight, okay. So weight could be like whether you have some prestigious customer, right? So you wanna give them more weights, right? So when you sample. Any questions? And any other questions? Right. So AJ value is higher than your sample, flip the coin with higher value. But again, you will be canceled out with S, right? So you can see that as your sample goes on, right, the probability that you take the later value, probability is going to be reduced because S is increasing. Okay, so next is counting a given element. So this is called a Morris algorithm. Okay, and again, so this only has a theoretical value because in reality, counting is very simple, right? You have an integer, 32 bits or 64 bits. 64 bits will always be enough, okay? And just count it, right? So you just add the increment the counting, okay? So, but here we have some theoretical value because we can use the log n bits, okay? So, log n is already quite close to constant, right? So log n is even smaller. Right? So this is like your n is crazily large, right? So 10 to the power of 100 or something, right? So then this makes sense. Okay? Otherwise, this only has theoretical value. It doesn't have any real value. Okay? Log n is very small number. Okay? You can create a sketch that memorize a count of some element, right? Whenever you see a string, you see an apple, you +1, right? Then you can get the count. That solution will take log n bits. Okay, if you want to just use log n bits, how do you do that? So here the idea is this: we want to keep a value k. This k will only use log n bits instead of log n bits, right? So then you cannot keep the value of n directly, right? Because if you keep the value of n directly, then it will use log n bits. K is log n. Now I want k to be log n. So what I can do is we want the number of currencies not to be n, not to be k, to be to the power k. Right? Then k equal to what? Equal to log n, log 2 of the number of currencies. Okay, and you know that the number of currencies itself only needs log 2 bits. Okay, so that's why it's a log log. right? So that's the idea. So instead of using k to represent the number of times, you want to use a k so that 2 to the power k, 2 to the power of k is about the number of times. Right? Again, so don't even use it in reality. It's just an algorithm showing that you can design some fancy space-saving method. Okay. In reality, just to maintain a 64-bit counter, and whenever you see your item, you increment. So this problem will go more complicated when you are not counting a given element. You're counting many, many different elements. Let's say for Amazon, they want to count each product, how many people are buying. Or for Google, each web page. Right? There are so many web pages. But how many people are watching them, viewing the web page? That can go way complicated than just a particular given element, right? And for that, you will see that in our second written assignment. So what I'm thinking is that we will just have 2 written assignments and we go to the final project, which we will announce in the classroom next week. Okay, we will skip the last minute project because the time is, it's almost it's already April. Okay, so we will probably skip the 1 minute project. Okay. So the solution of counting k, the algorithm of counting. Okay. Let me see. I think I should move on. Okay, so starting with k equal to 0, right? The counter starts with 0. When you see an item, you add a k by 1. But you don't always add a k by 1 you see an apple. Okay, what you do is you see an apple, then you add increment the k with probably 1 divided by 2 to the power k. Right? So which means if your counter, this k counter is higher, then the probability that you increment the counter is lower, even though you see the apple. Okay. So then you can estimate the occurrence count as 2 to the power k minus 1. Right? It's kind of close to 2 to the power k. This is almost equal. Right? So why this is meaningful, right? Why we can do this? Why it can reflect the actual count? Okay. So just think about this is a proof sketch, right? Not strictly. Just think about how we do this, right? So it will take 2 to the power k occurrence before k is incremented. Okay. So how to see that? You think about it. Right? So let's say now our count is k. That means in expectation, right? So initially you have 1, okay, because k equal to 0, 2 to the power 0 is 1. Okay. Then after k becomes 1, right? You increment k when you see an apple, the probability is only half, right? You need to see 2 apples to increment to 2, okay? And after that, right, your k equal to 2, right? Then 1 by 4, okay, the probability that you see an apple and you increment the k is 4. It means you, on average, you need to see 4 apples before you increment k equal to 3, okay? And by doing this, you can show this is, something like this, right? And so you know this each time you time 2, and you can use this formula to compute the summation. Okay. When you're at k, in expectation, you should see so many apples, right? So this is your number of occurrences on the left-hand side. And so k, if you have a counter k, now you can estimate the number of occurrences related to 2 to the power k minus 1, right? Again, there's some inaccurate part, right? You can only estimate to the level of 2 to k, in the order of that, 64, 128, but maybe it's actually 95. Okay, then you can only be in this order to be accurate. You cannot get the exact number. Okay? This is good only in estimate the order of number of occurrences, right? The difference can be twice different at most. Any questions? All right, I hope this is good. All right, so next is count mean sketch, which is for counting. Here we count 1 element, right? So now we want to count all elements. This becomes way complicated, right? So you think about it, right? So you have so many web pages, and how many times people visit each web page, right? Or you think about Amazon product, what's the number of items, right? Purchased by each customer, by the customers, right? This can decide the inventory or ranking web pages, etc. So this is gonna be more interesting and more complicated. So you will be self-studying this link and to understand what is count mean sketch. And after that, you will be completing the second written assignment where we have a question on that. So we will skip this in this lecture, but it will be in your assignment, just like the proof for the Chernoff bound on the left-hand side. So the next thing that we study here is to count the number of distinct elements, right? So so here we are saying that you see apple, orange, 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 then it's two distinct elements, apple, orange. Then you see pineapple, banana, then it becomes 4. Okay. It can have a stream of many objects, but you are counting how many different elements here in the stream. Okay? You don't double count the same element. So if you want to get the exact number, right, this is going to be, very difficult. Okay, but we do have a space upper bound, right? So you at most use so many bits to count that number. Right? So first is OM space. Right? The reason very simple. You can use a bitmap. Right? So you have apple, orange, banana. Each has a 1 bit. Right? So you have a 3-bit bitmap. Okay, whenever you see an element, you give a set that bit. Okay, altogether. Finally, just count how many ones in the bitmap you see. That's how many distinct elements. Okay? So this is one solution, right? So you can count the distinct elements exactly, right? So we will see how to approximately count that later. So the second upper bound is n log m. Okay, so this n log m space is also very simple. Right? So you just keep whatever you see. Okay, and each item can be represented by, because the value is taking a domain of 1 to n. So at most log n bits, and you have n items. You just remember all of them. Later you just count them offline. This is memorizing all the data, but this is gonna be more space consuming, right? Remember the whole stream, okay? Instead of counting a bitmap count, right? So for n, when n is smaller than n, much smaller than n, you use the first method. When n is very small, right? You only have, let's say, just count how many items you purchase in 1 year. Maybe the possible items in Amazon is maybe 1 billion or 1 million. Okay, but you only purchased maybe 200 items. So in that case, maybe this is more meaningful. So you keep n, but this m is 1 billion is log. Okay, otherwise you will need OM, which is 1 billion. Now you have 200 times 30. This is 60,000. So it's much better. So basically, there are 2 upper bounds. Right? You just see whether some make sense. Right? If your n is way less than n, maybe this is even tighter. Okay. So, but these are not good, right? So remember our requirement for sketch is log mn, right? Log mn, right? So here we don't want a linear, right? So here it's more than linear actually. It's at least linear. Okay. So this one is linear. This is linear by another factor of log n. Okay. So we wanna be space efficient, but we still wanna count the number of distinct elements with reasonable accuracy. So how can we achieve that? Okay, let's think about assume that we have a set. This S is a set of items, just like our samples previously mentioned. Right? We sample uniformly from the different items. Okay, that we see. And let's think about this, right? So if we assume the items are uniformly distributed, let's say we have 3 items. Okay, they are uniformly distributed among the m items. Here we have m items, right? And they are really super evenly distributed. Then we will have 3 items like this. Okay? And what's the minimum element here? Right? What's the minimum element here? This will be m by 4. Okay. So you have 3 items, right? So this is 1 segment, 2 segments, 3 segments, 4 segments. So you will have, if you have 3 items, you multiply 1, become 4, right? So this is the value here, m by 4. Okay. So this is the intuition that we are looking at. So for example, if you only have 1 sample among, and it's uniform, right? It's perfectly uniform among m items, then the 1 item is in the middle, right? Of course, it's m by 2. Right? On the other hand, if you have two items, right? So the 2 items should be evenly distributed. You have 1 item here. Let me see. You have 1 item here. You have 1 item here. Right? So this is the smallest item here is m by 3. Okay. So basically, you know, +1 is 2 and 3. Okay. So in general case, you have this, and the small item is about this size. Okay. But this is expectation because, you know, you're assuming it's uniformly distributed along this range. So you can estimate, let's say expectation is mean and we really achieve this mean. Right? So then you can compute your number of distinct elements, right, as well. So we're assuming we have, so this S is a distinct element, okay, that you sample from all the n, and it's uniformly distributed, okay. So right now, we assume it's uniformly distributed, okay. We will see later how we can achieve this truly uniformly distributed, okay. So if you just, you know, move this to the right-hand side, S +1 equal to n divided by me, okay. And because it's +1 into -1. So you can estimate S approximately as this value. Okay. Usually, you know, you are estimating very large number, right? How many distinct 1,000, 2,000, -1 can be given. So put simply, what you need to do is you just check the stream of items and you keep the minimum item, okay, that you see so far. Right? Once you have the minimum item and you also know how many items are there, like selling by another, right? Then you just use that divided by the minimum item you see. You can estimate how many distinct items. Okay? This looks pretty crazy, right? Of course, this is not correct. Okay, but we'll show that this can be correct with certain probability, and then you can use a Chernoff bound. You repeat this. Remember, we can flip a coin each time we get an estimate, and this estimate maybe the average value is correct, but there's a big variance. Then you can bring it down by law of large numbers. Okay. Any questions so far about this setting that we are talking about here? I hope that the intuition is good, right? So later we'll prove things strictly, right? So this looks crazily, you know, kind of crazy, right? Why is this? Intuitively, it's okay, but each step is not rigid. Okay, we will show. So firstly, what we solve the problem is that what if we say that maybe your item ID is from 1 to 1 billion, okay? And I buy 100 items, but the items only have 3 distinct items: apple, orange, banana. Right? How I can make sure among the 1 billion items, my apple is around here, my orange is around here, and my banana is here, so it's kind of evenly distributed in the ID list. Right? You count. If your apple, orange, and banana are always like ID 1, 2, 3, it's always in the front. So when you do this is you can shuffle them, right? Shuffle them by hashing, so that you shuffle to a new ID. The new ID is kind of random in this way. Okay? So that's how you guarantee this uniformly selected. But that's also the idea of randomized algorithm. You want to avoid the worst case, right? It happens that your idea are very small. Okay. So again, this algorithm is good because all you need to do is just to check what's the minimum item you see in the stream, right? And need the log n bits. Okay. And again, so here I want to make it clear that this mean when we talk about ID, we are already assuming it's uniform distributed, right? And we say we need to hash it. Right? Later we will see that we will use different hash function, okay? And this mean will be different, okay? For different hash function. This time apple is the main, next time orange is the main, etc. Okay. So by doing that, you kind of have independent samples that you can bring down by law of large numbers, okay? Or you finally compute their mean to estimate. Okay, now let's look at how to guarantee that the different items in our stream, actually, we can shuffle the ID to be randomly distributed in the domain. So we are using the concept of universal hashing, which you probably already see that in your introduction to algorithm course, or something like in college, or I'm not sure whether advanced algorithms are teaching that also. So this method is called FM sketch, right? Using the capital names of these two people. Okay. So in FM sketch, the set S is a set of items you see currently in your stream, right? And which means we don't duplicate items, we don't count twice. Right? So we just, if you have 5 apples to an orange, that's just the apple and orange, right? Okay. But these two may not be uniformly distributed in 1 to n. Okay. it's maybe just the first one, the second two. Right? Then you always get one. Okay. Right? Even though you just see apple, orange, but if you use this method here, right, you have 1 million different items, and you always see apple, orange, right? You divide by 1 or 2, and then you will overestimate because only see 2 items, but this value is here, so that's not good. So in order to do that, we want to shuffle apple. Right? Apple originally the ID is 1, but we randomly shuffle it to be 500,000. Right? Okay, something like this. So this is called a randomization to avoid the bad cases like we discussed earlier. Right? But this cannot be guaranteed always. Right? So we want a WHP, which means with high probability, we will avoid the bad case. Okay, but again, you can still have a bad case, just like our binomial trial. Right? Each time you fail with certain probability. Then you can try many times, like in our Chernoff bound, right? And then you still fail, the probability is going to be really low, decrease exponentially. So that's the idea of using this kind of randomization. Okay. So you can shuffle the input from the original domain 1 to n, right? Apple 1, orange 2, to a new domain. And there maybe apple is 500,000, orange is 2/3 of a million, right? So then they are not totally, you don't have the worst case that we talked about. Okay, so that's the intuition here. So then in the FM sketch, we track the minimum hash value. Okay, we hash it. Right? We first decide a map like this. We track the hashed value. Right? So like 500,000 and 2 by 3 of a million. Right? So 500,000 is small. And the main here is actually the hash value because we assume it's uniform distributed after hashing. Okay. Right. So it's for the universal hashing, we need to use a proper hash function. Okay. So let's take a look at how we can construct. So firstly, why does such hash function exist? Right. Secondly, right, because we have an independent requirement. Right? So different hash, they should be independent. Okay. The second is whether we can achieve such an ideal hash function that we want. Okay. So these are both achievable. So firstly, we can have a set of hash functions. This is called a hash family. Right? So you can see this is a set of hash functions. Right? Say every function is a mapping from an old domain to a new domain. M usually a little bit larger than small m. Okay. And but we want to satisfy so-called pairwise independent hash function. What does that mean? So what is pairwise independent? This happens if for any old domain values x and y, 2 different values here. Right? Firstly, it should be uniform. Right? The probability that your apple map to 3 and your orange map to 3, they are both equal to 1 by n. Right? So basically, we are saying that the probability that your x map to a value and the y map to value should be equal. Okay? And we are saying here, for simply, let's say 2 can be mapped to 0, can be mapped to 1, can be mapped to 2, and this is uniformly mapped. Okay. Ultimately, we will map to 1 value, right? So some particular value, let's say I. But the probability that you equal to I is 1 by n. Okay. This is what we say. Because for any value, it map to a particular other value, the probability is 1 by n. So this is one requirement. This only guarantees this is uniform. Okay. The second is called independent. Independent. So what does it mean by independent? So if you remember, you have 2 random variables, A and B, basically. Okay. When they are independent, then we have something like this. So okay. Let me see. Right. So up there, well, independent, we have this. Because if they are dependent, then you have something like equal to PA times PB, conditional. If you're really equal to PA, PB, then it's really independent. Okay. So we want to show that 2 events are independent. So firstly is x is mapped to I. Second is y is mapped to j. Right. So here is what we see. For a hash function from this hash family, what's the probability that it will map your x to w and the y to z? X, y are here, okay? W, z are here. Okay? So we will show that the probability equal to 1. We wanted the probability to be 1 divided by m squared. Why? Because you know this probability is 1 by n, okay? And this probability is also 1 by n, okay? So we say PA is 1 by n, PB is 1 by n. If your PAB is 1 by m squared, then it means A and B are independent, right? This independence means, hey, how likely this value will be matched to this and this value matched to this? They are independent. They are no correlated. The fact that you are mapping to here will not impact the probability that you map to here, okay? When you sample a edge from this family. And our goal is to find such a family that can satisfy these two requirements. Any questions so far? If not, let's continue. And we can take a break after the universal hashing. Okay, let me see how many slides. Yeah, we probably still have 5 slides, and we will take a break, 10-minute break, and we will continue. So no, we say that hx and hy are statistically independent if we make sure they are 1 by n squared, because each probably is 1 by n. Okay? So we can construct an exam function easily, actually by this. And so here we are thinking about the integer field, say p, where p is a prime. If that's the case, you know, we can define, let's say p is 7. Right? If p is a 7, then you know the p is from 0 to 6, okay? 0, 1, all the way to 6. We can write it as a bracket 7. Okay, and then we sample all of these values a and b from the p, okay, from the 7. Then they have a is from 0 to 6, b is from 0 to 6. Okay. Right? This x is also in ZP. Basically, everything is in ZP. Right? If we sample this p, right? So if we have this function, this is a linear function, right? But after taking the ax plus b, right? The result probably will be larger than 7. Okay, larger than equal to 7. But we will modulo 7 again. So the ultimate value is again between 0 and 6. So so to keep such a function requires log m space, because a and b are within n, right? Because you know it's 0 to n minus 1. Okay? You just need log m bits. And if we have m equal to prime, we have this property. Okay, we can guarantee there's a probability that you will map to any value is 1 by n. Okay. So anyone know this theorem? It's a number theory, right? So basically, if you are in ZP, okay, ZP, let's think about a P which is easy to play with. Okay, let's think about the prime is 5. Okay, and let's give two random values. Let's say 1 is 2, this is 3. Okay, so let's just try to see what will happen here. Okay, this can be proved for any prime number. Okay, any prime number, 2, 3, 5, 7, 11, etc. Okay, so here let's consider a bunch of values here. Right, we consider x. It can take a 1, 2, I think it's 0. Right? So because it's in 5, say 5, right? It's a 1, 0, 1, 2, 3, 4. We can take this, x can take these values, right? Because we modulo 5. Okay, now let's take a look at what if we for a particular hash function a be materialized to 2 and 3, which is in this domain. Okay. Right. Then what will be HAB? Let's call it y. Okay. What will be the y value? Who can tell me? This is not difficult to compute. Right. When your x is 0, what will be the result of this? Who can tell me? I think this is very simple, right? 2 times 0 plus 3. Right? What's the value here?
3.
Yes, 3. Right. Okay. Now what if x equal to 1? 2 times 1 plus 3. What's the value here?
5.
5, but because it's modulo 5, so it's 0. Okay. Now let's.
Oh yeah, that's right.
Yeah. X equal to 2. What will be the value here?
7.
Yeah, 2 plus 2. 2 times 2 is 4. 4 plus 7. Right? But modulo 5 is 2. Okay. And then now let's consider x equal to 3. Right? What will be the result here?
4.
4. I didn't count it, but maybe 4. So 3 is 6 and 9. Right? 9 minus 5 is 4. Okay, yeah. And what if it is a 4? What will be the value here? The answer is no. So x equal to 4 is a 4. 2, 4, 8. 8 plus 3 is 11. Right? 11 is 1. Okay, because minus 10, 2, 5. So what we have is, as long as this n is a prime number, your y is going to be a Sheffrin length. Okay, it's okay. So you can see still these 5 numbers, but everyone pure ones. Okay, maybe you use a different. Maybe this is 3. This is maybe 4. Then you will get another value. But again, this is a Sheffrin length. These 5 numbers. Okay, in your AP. And there's a theorem to guarantee that. Okay, you can prove that. So. But anyway, so this is a guarantee. Okay, you can see that the probability that you map to a value, right? So 1 will be mapped to 0, right? This probability, and the 1 will be mapped to maybe for another function will be mapped to here, right? Different values. Okay, so you can see because it's a random shuffle, right? So you shuffle to a new position, the probability 1 by n. You have that guarantee. But this only holds if your n is prime. It's okay. So the second is to compute the independence, right? To compute the independence, I see a chat. Oh, the question is why it should be a prime number? Because only when m is prime numbers, you can show that after this kind of mapping, it's a shuffling. Okay, if it's not a prime number, you cannot guarantee that. Maybe 2 values in your original x domain will be mapped to the same value in the target edge. Okay, you can easily construct such a thing. Okay, so there's a theorem that you can prove, right? I can actually find this proof for you guys if you're interested. Just send me email, let me know. Okay. But for a non-prime number, you cannot prove that, and you can find a counterexample. And so, yeah, what if x is not equal to y, right? So x is not equal to y, you can show that w is not equal to 0, right? Because it's a prime, so each number will be uniquely shuffled to another location in the H domain. Okay, so if x is not equal to y, then w and z must be different. That's what we just showed in Z5. Okay, and because this reason, if you think about, you write it as a linear equation. Right? So hx is ax plus b equal to w. Okay. This is ay plus b equal to z, right? If you write this. Okay. And this can be written as this linear equation. Right? It's x1, this y1, right? The ab is coefficient here, and the y is w is that is. Okay, so you can write like this. And this matrix is invertible. This is invertible because the rank is not 1. The rank is 2, right? Because these 2 rows are totally different. Okay, the reason is x is not equal to 1. Okay. So this is invertible. You can left multiply the inverse matrix. Okay. Then, so basically for each WZ, you will find a unique A, B, right? Not 2. Okay. Because of this reason, so you have how many combinations of WZ? Right? So WZ is all from this domain. Right? So then each WZ you will find a unique AB. Right? It's a combination of A can take n values, B can take n values. Right? So it's m squared. So the probability that you can map, so this is our conclusion. The probability that you can map to right, one to a value, the other to another value is really 1 by m squared. Right? Because you have it's uniformly distributed, invertible, right? Each one mapped to unique. You have m squared amounts. Okay? So the uniform distribution target is really 1 by m squared. Okay. So far we require the m to be prime. Right? So what if m is not prime? Then you will find a p that is prime, slightly larger than the next largest. So you count from m, because your domain you have n elements, but that's not a prime. So you will maybe it's 10,000. That's 10,001, 10,002, and you try until you find a prime. And you can prove that the prime will not be very large. Okay, it will be only slightly larger than. It will not need to be like twice as large. You can easily find a prime that is larger than a particular number. If there's theorem to show. Maybe just count 3 or 4 values, we'll find it. Okay. And so again, so by this time, maybe you have some wraparound problem. So because you want to map these two here, but we say, hey, you need a prime to here. So because this reason, some two values will be mapped to the same value in the middle. But that's fine. Okay, so we have some small sacrifice for a few items, but overall, it's still respect the previous theorem. Okay, especially when your m is big. This is fine. So so pairwise independent hash function is also called the two universal hash function. So we can go beyond the two universal. We can go so-called k-wise independent. So which means one value mapped to a I1, another value I2, k to k. Right. So basically we can have k items here, map k different values to k new different values. Okay. So this is more strict, right? So because I don't just need any two k to be independent. I need any k subset to be independent, to be a product. So this is called a k-wise independent, which is more strict. And likely we can define a universal hash function like that. So because this is 1 by m, this is 1 by m, this is 1 by m, k of them. So the product, if they are independent, should be 1 by m to the power k, which is this. Right. And so this looks pretty crazy, right? So can we really have a k universal hash family? Right. So the answer is actually it's very simple to create that. So we do the same. Okay, so here we are still having a module m. Okay, we still have the module m. But we are defining for example, if your k is 4, then we need to have a polynomial mode 3. Okay, if your k is 10, then mode 9. Okay, because you have the constant thing. For example, for pairwise independent, right? So k equal to 2. 2 universal, k equal to 2. So this is 1. That's 4 is 3. 2 is 1. So that's why you have our previous one. Okay? Ax plus b. So how to see that this makes sense, right? So just think about our previous one, right? We are creating a linear equation like this, right? Now you think about we have x, y, two different values to wz, right? So now assume we have k different values, right? So we said we have I1, I2, I3, right? We have k different values. If that happens, so I have one value which is maybe A1, A1 square, A1 cubic, okay? And then we have, this becomes constant, right? Because these are the values we want, okay? And then I have a W1, okay? Then I have A2, A2, W2, right? And because we have 4 y's independent, we have 4 equations, okay? 3, 4, right? So these are the 4, these are linear equations where the unknown variables are 4 unknown variables, okay? And we have 4 equations. So you will find a unique solution. Okay. So when it's unique, then it's n to the power k, 1 by n power k. It's uniformly distributed. Right. So by using, if you want a k1 independent, you have a polynomial to the power of k minus 1. But this is a hash family, right? Which means we're saying that each coefficient is uniformly randomly sampled, like a flip a coin from your ZP. Okay, this is also randomly sampled. Only by doing this, this function will be random. Okay, randomness. It's a randomly sampled from the hash function. So if you look at our notation here, this probability comes from how you sample a hash function from the hash family. So this should be strictly following that ZP for each coefficient to sample. So so like this, A should be randomly sampled from this domain, B also randomly sampled from. Okay. And 2 different times, the H will be different. Okay, the shuffling of the item to the new domain will be different. Okay. All right, let's take a look at the time. Okay, so it's 6:52. Then let's come back at 7. Okay, take a close to 10-minute break, and then we will continue about FM sketch. FM sketch needed 2 universal hash on family. Okay, we'll see that. Any questions? Okay, in that case, I will see you in less than 10 minutes. Okay. Again, this is a randomized algorithm, which is pretty difficult, and as long as you get the idea, that's good. Okay. Okay, let's begin. Yeah, so now assume that we have mean. We FM sketch. What we do is we look at the stream, right, and we hash each value we see, and the hash value we will keep the minimum value, which means whenever we see a new item, we hash it and we see whether it's smaller than the current mean value I see. Right? If that's the case, I will replace it, okay, with the new minimum value, but it's hashed value, okay, so not the original value, not the original Apple ID or origin ID. It's the hashed Apple ID or origin ID, okay, using the 2-wise universal hash. And D is really the distinct number, right? It's the size of the set S of distinct elements, okay? And we want to show this, right? So we want to show that if you estimate using your domain size divided by mean of the hashed value, right? It's gonna be within D divided by 6 and 6D, right? So this looks not so interesting, right? But we want to say this is almost equal to D, right? But if we replace 6 with some very small number, epsilon, right? With 1, right? Then that is interesting, okay? If 6 is becoming something 1, then it's exactly D equal to this. Right? So here 6 is just a constant, okay? We can replace 6 with any C. That can make it very close to 1. It's like 1 plus epsilon, okay? We can show some similar theorem. It's just that now if it's 6, we will show that the probability is larger than 2/3. Okay? If it's some C, then it will be a function of C, which is again a constant. The constant is depending on C. Okay? When the C is equal to 6, if 6 is 2 by 3. Okay? The proof we will see later holds for any C. And the C can go very close to 1. But when you go closer to 1, 1 plus epsilon, when epsilon is very small, then the probability will drop. Okay, that you be super tight will be low. But again, it's a constant. And according to what we're discussing, Bernoulli, the Chernoff bound, right? Even if each time you try, okay, each time you try, it's probably very low. That is fine. Okay, you can try many times. As long as each time you try, the probability is constant. Okay, and then if you try many times, n times, okay, this is exponential decay because this is a q, which is less than 1, and try enough times, the failure probability will go very low. Okay, so our goal is just to show that for any constant C and C here, this will be a constant. That depends on C, but it's a constant. Okay, it's a this 6 you can think about 1 plus delta equal to 5. Okay, this is a function of delta. The reason we just look at 6 is because it's easier. We just have a concrete number, then you can get an intuition. So now let's prove this. Right? So it's within a factor of 6 times from the number of distinct elements on both sides. Okay, the probability is going to be at least 2/3. Right? So in order to prove this, we'll prove two things. Okay? This is one thing. This is the second thing. So what we are saying is that let's think this is a number axis. Okay, and so this is d by 6. Right? This is d by 6. This is 6d. Okay, d by 6 and 6. Okay. So what if, let's say, we have your value. So your value is larger than 6d is this, right? This one. And your value is smaller than d by 6 is. Okay. We say, hey, this is less than 1 by 6. This is also 1 by 6, right? So this is less than equal to. That's less than equal to 1 by 6 on both sides. That means this value will fall in within this range, right? Within this range. So probability is going to be at least 1 minus 1 by 6 minus 1 by 6, okay? Which is 2 by 3. Okay, because this is 1 by 3, basically. And this is smaller than this is larger. Okay? So basically, if we can prove these two, then we can also prove this. Right? So this is why we just prove these two. this is actually stricter. Right? There are also other cases that can make this hold, but if you can prove this, this definitely will make this hold. Okay. Right. So first, let's look at this side. Right. So 6D. Right. So how can we prove this? So yes, this is just to do some simple, like a move mean to the right hand side, 6D to the left hand side. Right? So we'll get it. Okay. And what does this mean? Right, this is the interesting part. Okay, what does it mean less than this mean? Right? So what does it mean? Mean is the minimum hash value. Right? So whenever you see a number, right, you hash it, okay, and you keep the minimum value. Right? So let's consider for all the stream, right? We take the set of different items. There's an S of them, right? They are like B1 all the way to B. Let's say we have D different item, BD. Okay, a particular item BK, right? Where we hash it, the hashed value, what's the probability that hash value is less than this, right? So you think about these D distinct elements, right? And the hash to 1 to n, okay? Right. So maybe B1, right? B1 is hashed to here, B2 is hashed to here, B3 is hashed to here, and BD is hashed to here, right? So what does that mean by the minimum hash value is less than this, right? Which means this thing is less than n by 16. Okay. It's okay. So that means at least one exists some k, some p2 for example. It has to this side. Okay. So these two are equivalent. I hope you can see. Right. I think the notation is a little messy, so let's reconsider this again. We're doing some. Okay. So this is 1. Okay. If we are n. Right. And we have different values in the old, different distinct value here, right? And they are hashed to different places. Okay. And we have a bar, right? So we have a bar that we want to cut. Okay. And this bar is this value. We want to say, hey, at least the one, there exists something that is map to less than. Okay. So you can see this is equivalent, right? So if you cannot see that, let's just think about this direction. Right? So if you have anything that is less than this, of course the minimum is less than this, right? Okay, this is this direction, but we can also show this direction. Right? If your minimum is less than that, of course you have something. Right? Minimum, of course, some of them. Okay, so they are equivalent. Right? Next, let's think about this term. Right? So this is actually using a union bound. Okay, so we are saying, hey, what's the probability that the first distinct element is hashed to this side? And what's the probably the second distinct element B2? It has to this side. Right? And also altogether we have D different. Okay? So each event, right? B1 is less than this event, there's a probability. Okay? HB1 is this. B2 is this. Right? So exists something that it holds, means that at least a sum of them happens. Okay? You can have 2 or 3 events. Right? So this is B1's event, this is B2 event, this is B3's event. They can overlap. Right? So at least some of them happens. Right? So it's the total area in the William diagram. Okay. So this is going to be less than or equal to this is union bound of each set, each event probably. Okay. So now. Okay. Any questions so far? Right. So if this is fine, now let's take a look at what's the probability here. Right? Because remember we use the universal hashing, right? Which means the probability that from B1, for example, to anywhere, it's a uniform. Okay. Because it's a prime number, and any position is like it's uniform. So then the probability that you fall in this range, you think about what's the value here. The value is this, okay, n by 60. But what's the total domain? The total domain is n, okay. N. So the probability is really what? It's a 1 by 60. Okay, I hope you can see this. 1 by 60. Right. So now you know this this holds for area of the term, right? It doesn't depend on the r. Okay? So you have D times this, 1 by 60. And then, they cancel. So this M cancel M, D cancel D, okay? And that's why we prove this. It's on the right-hand side, it's 1 by 6. Less than, right? Okay, any question about this proof here? Hello? I think, Kalyani, do you have any question? Because I see. Any questions? I can not hear you clearly. So maybe I can mute if you want to ask it, just unmute yourself. So I know you're asking. Okay. All right, so now this side, larger than 6 times the distinct elements, right? The probability is low. Okay, we know that. Now what if smaller than 6 times, right? The probability of the distinct element D, right? This is also low, okay, less than 6. Okay. How can we see this? Again, we are doing something similar. Right? So we just rearrange this, we look at this. So mean to the right-hand side, D by 6 to the left-hand side becomes 6 by D. Okay, right? So here you can see that what is the mean, right? So this is again, right? So your minimum value is larger than some particular value. It means for any of the original distinct value IDs, right? After hashing, they are all larger than this. Okay. If they are all larger than this, of course the minimum is larger than this. So this direction holds, right? And the minimum also holds, right? Because the minimum particular B that is hash, right? Because when we look at each element hash value, right? So there must exist some B. The smallest is larger than, of course, average one. So these two are equivalent. You can see this, right? I hope this is fine. If this is fine, then we can use indicator variable. So we need to define this in a reverse way. Right? So originally, we say, hey, if this holds, then it's successful. But here we are saying, hey, this is 0. Right? Otherwise, this is, we keep this in. Right? So we are defining in a reverse way in this setting. And then if we define y equal to the summation y, that's the first item is hash 3 larger than this, the second larger than this, right? So if this holds, it's actually 0. So you don't add anything to y. Okay. Only when some bi after hashing breaks this inequality, then we have 1. Okay. So the probability that for all of them, right, they do not break the probability. It means all of them are 0. D0 sum together, which means y is 0. So here we wanted the probability, actually, if we define this indicator variable like this, then actually the probability y equal to 0. This. So now let's look at what is y equal to 0. So actually, let's just look at the next step. We can prove that, or we can show that this is upper bounded by this. Right? So how can we see this? Let's consider this a number, right? Let's say this means the number of y. And this is a y equal to 0. Okay. So here we are saying, what is this range? Okay, let's look at this one. So there are 2 sides, right? The first side is, let's say this is EY. Okay. So the first is y is farther from EY by a side of EY. So one is you are 2 EY. Okay. From here. The second is again you are farther from EY by EY. Okay. Of course, you can see that the probability this is the area of these two sum together. It's gonna be upper bounding the probability that you are exactly this bar. Okay, so that then you can see that this really hurts, right? So this y equal to 0 is a particular value that satisfies this. This is more broad. Is this okay? So why is this interesting? Because this we can have the Chebyshev inequality, right? So how far away you are from the expectation, right? And larger than a particular c, right? It's gonna be equal to variance divided by c squared, right? Bounded by variance divided by c squared. So c is also EY. Okay, so we can show that this probability is bounded by this bar, and we will show this bar is 1 by 6. Okay, So this is what we are trying to do here. Okay, so firstly, let's come back to yi that we defined, right? So what's the probability that y equal to 1? So so this is saying, hey, this is your 1 to n, right? And this is 6 by dn. Right? So this is d is a large number. So this thing now you have 6 by dn, which is here. Okay, this value is 6 by d. Okay. So if you're larger than that, it means you are here. Right? So it's 1 otherwise, which means you are here. Okay. Right. So the probability you are here compared with this is really 6 by dm divided by n. N can cancel. So this is 6 by d. Okay. I hope you can see how we derive this. Right. So by saying that EYI equal to this, right? Y using linearity of expectation, right? So EY equal to summation of E this, right? We have D such values summed together, which is 6. Right? D times divided by D and times D cancel. Okay. Next, we are using our famous conclusion, right? So now you should not even need to expound it from this step. You should go directly from here to here. Right? So basically, the variance of a random variable equal to the random variable square, takes expectation, minus the expectation square. Okay, that we see it a lot of times already. And interestingly, because we have this y, okay, it's what? It's 0 or 1. So y1 square is what? 0 squared is still 0. 1 squared is still 1. Okay, so y squared is equal to y. Okay, I hope you can see. So what we can just write as y. It's the y squared, right? So now expecting y1 minus something, right? So minus something, this is a non-negative number, square. Okay, so of course, if you remove this term, you will be above ey. Okay, I hope you can see that. So now here, what we proved is this. Right? So this is for a particular one. Okay, a particular one. Now we are using the fact that for different yi's, right, they are coming from the h function, and we show that it's a pairwise independent. Right? If there's a pairwise independent, if you remember, we also have the linearity of variance, which means the variance of y is equal to variance of y1, variance of y2, variance of yd, right? D of something. So the d times this. Okay. Okay. And this thing is going to be less than or equal to ey. Right? So it's the reason because so ey itself is d times this. Okay, and we have the less than or equal to sign. Okay. So that's why we get it. Right. So here then we have this conclusion, because you can see here, variance is less than the expectation for this y. Right. So if we make it a little bit larger to ey, right, then it's this sign. Okay? And then this ey cancels this square, so we get this. Right? And keep in mind, this thing is 6. So this is really above the masses. Okay. So this is how we prove this. Any questions so far? Oh, so there's a student asking the question, so why this thing equal to this thing, right? So the reason, as I explained earlier, is because y1 squared is equal to y. Okay? Because y is 0 or 1. Okay, 0 squared is still 0, 1 squared is still 1. Do you answer your question? Come on. Okay, yeah, so if it's okay, let's continue. Feel free to ask questions during the process. Okay. All right, so let's continue. The next is so previously we see the distinct element, right? So you have a string, how many different elements are there in the string. Next, look at the majority algorithm. Okay? Majority means, hey, if I have a stream of items, right, we want to see whether some item appear more than 50 times, 50% of the time. Right? If I have 10 items, right, whether there's some item appear more than 5 times, like 6 or 7 times. Right? If that is the case, really there's some item that appear more than 50% of the time. What is that item? Right? So this is the question we want to ask. So we can show that if you really want to answer this question exactly, there's a space lower bound. Okay, there's a space lower bound. So this is have to be gonna be at least a linear. So the omega is like a big O sign, but it's a lower bound. Okay. So so how can we show that if you want to exactly answer this question, whether there's an item that is a majority? If so, what is this item? Right? How do we know that at least if you want to answer this question without any mistake, in any case, right, you need at least a linear space. Right? How can we show that? So here's how we answer this. Right? Assume that, let's consider a stream of data, and remember this stream has a size n, which means so far we see n items. Okay. So what we can do is we can cut it into 2 halves. Okay, we can cut it here. Right. So so each has a so each has 2 n by 2 items. Okay. So we are saying the second half are all S prime, which means here this is all S prime, S prime, S prime. All of them are S prime. So basically we have S prime, S prime, S prime. Okay. So this is what we have. And now let's consider 2 other streams. Okay. So this is one stream, right? And this is another stream. Okay. Right. So now let's think about it. So we assume these 2 streams are different. Okay. We consider these 2 streams are different. So S1 and S2. So let's assume this is S1. The first stream is 1. The second stream is 2. And then let's assume, even though they are different, our scattering algorithm, finally, when we see these n by 2 items, we have the same content in our memory. Okay. So that means we don't differentiate. Right? Will that make a mistake? That's our question. Okay. So here, it really depends on how we choose the second half, right, S prime. Here we assume that S prime is a particular item that exists in S1. Right? That's transient level. Okay. This item exists in here. That's in S1, but not in S2. Okay? Not in S2. So such a point must exist. We must be able to find such a S prime and put it, replicate on the second half. Okay? Because S1 and S2 are different. Okay? There must be an item that is different. Okay? Otherwise, it will be the same stream. Right? So if this happens, actually our solution will be wrong. The reason is very simple. Think about it, right? So here, if we have another S prime in S1, then this S prime will be majority. So this answer is yes. S prime appear more than 50%. But for the second, it's going to be wrong because there's no S prime in the first half. The second half is prime. So S prime appear for exactly 50% of the times, not larger than 50%. And there's nothing else that can be more than 50 times, right? Because the other are, again, at most 50%, right? So you can see that if by this time we have 2 streams that lead to the same sketch content in the memory, right? Then we will make mistakes because then you pick a S prime here and have the second half of the stream, right? Then this particular case, you will answer things wrong, right? Because you can only give one answer, right? Whether there's a 1 or not, yes or no. Right? If you answer yes, right, and this is correct, but this is wrong. Okay? If you answer no, this is correct, but this is wrong. Okay? So that means we cannot achieve the correct answer all the time. Okay, with this case. Right. So now the question is really, so the problem happening in the first half of this. Okay, right. How many bits do we need to represent the first half of the stream? That's the question. Right. So the answer is that we need a 2 to the power of n, min n, right? So it's because this reason, right? If we need so many different numbers to represent this string, right? So then how many bits is log 2? So many different sets, right? So here we are saying the S1, S2 are different sets in the first string. Okay, and so here, because we are talking about even though S1 is a string, but we are talking about different elements, right? Whether we have an element or not. So they are different sets. Okay? So for this set, actually, if you have so many different kinds of sets, right? So you have A, you have AB, you have ABC, you have BC, etc. Right? If you have so many sets, let's say we have this K equal to this, right? Then how many bits you need to represent different sets? No two sets can be the same, right? Because if they are the same, then we can construct such a counterexample to make a mistake, right? Not to answer. So then we need a log 2 to this number, which is exactly m. Okay, is this okay? If this is okay, so the question remains is why we need so many. Right? So you think about the first half, we have n by 2 different items. Okay, then how many sets can you have here? Right? How many different sets can you have? The first case is if you have because you have n different items, right? So the set can have Cm1, right? Cm2, right? Which means among the m items, you take one item. The set is 1, then 2, plus Cm n. Okay. So if you think about this is actually 2 to the power n. Right? So you can have 2 to the power n different combinations of sets out of these elements. Okay. But maybe m is a super large number, right? We're much larger than the allowed item n by 2. Right? If that's the case, then actually you cannot go to all the way to n. You at most go to all the way to n by 2. Right? And if you count this number, it's actually 2 to the power of n. Okay, it's actually 2 to the power of n. So the way to see that is each item you can. So this is a combinatorial number. You can compute that. Okay, you think about it. So this is like you can have m different items. This is n minus 1 and all the way to n. Okay, so you can show that this is 2 to the power of n. This is in the case that n is much smaller than n. Then it's not dominated by n, but by n. So in any case, you want at least a minimum of these two numbers. Because n is smaller than n, then you are dominated by 2 to the power. Okay. So this shows that even for the first half, right, 2 by n, you need so many bits. For the whole stream, of course, you need more than these bits to be able to uniquely differentiate two sets that otherwise will make mistake. Okay? Will not be able to correct this. So this tells us that the space lower bound is already linear. Right? So we cannot exactly answer this question. Right? So next class, we will look at how we have a weaker problem and we can answer this easily. But we are not answering this exactly. Okay. Right. So that's all for this class, and we are not taking attendance today. Right, so maybe next week we will take attendance. Right, and we will also discuss the final project in the next class. Thank you, and have a good night. And any question? I will be here for 1 minute.
Yes. When will we have the other home assignment? The second one?
The second one will be right after the first one. I think this one will end on Friday or Saturday, right, this week. Okay. So next week we will have the second assignment. Will that be okay? Next week we will have the final exam and the second written assignment. And these will be the last 2 assignments and the final project. Okay.
Okay, thank you.
Okay. Any other questions? Yeah, I see a question in the chat. Oh, yeah, thank you. And yeah, if you have any question, feel free to send me email, right? And also talk to the TA in their office hours. Okay, have a good evening then. And I will upload this video to YouTube, and I will send an announcement so you can access it. Have a good evening.
Thank you, Professor.
Welcome.